Right. So what is Pell's equation? All right. Pell's equation. Let me erase these. Oh, by the way, test 1, the RSA is on test 1, but after that, like this and the Pell's equation about the cover, not test 1, that's test 2. So, just so you know. We finished test 1 material when we finished the discussion of encryption. Yeah. So what is Pell's equation?
That's 27, right?
Yeah, that's what, next Monday?
Next Monday?
I believe so. So the hilarious thing about Pell's equation is it's not Pell's equation. Pell's equation has at least been discovered as far back as, like, I think Archimedes. So like you can state there's a cattle problem of Archimedes, which somehow boils down to this horrible Pell's equation. So that's like millennia old. There were Indian mathematicians, Brahmagupta, that's probably wrong, and also I'm gonna butcher this as well. Basharakakachara, that's so wrong. Whatever I just said. Anyway, complicated Indian names, starting with the letter B, 2 of them. One in the 8628, the other 1150. They both studied Pell's equations. They came up with techniques for solving it, for understanding it. Then in Europe, in about 1600 or so, there was a fellow named Bruckner who studied this, William Bruckner, 1657. So Silverman, I'm currently looking at a chapter from Silverman's number theory. Silverman's always a contender for a book I choose, but, well, I don't know. It is what it is, but this is a friendly introduction to number theory by Joseph Silverman. This is where I'm currently talking to you guys from, because honestly, folks, the discussion of Pell's equation in Stillwell, it's just very technical, and it's hard to follow. And he talks about stuff about diagonal and side numbers. He's got no pictures. I have no idea. I mean, I've read the section and no, we're gonna follow Silverman here. It's going to be easier, and I think it'll make more sense. But anyway, Silverman suggests that it shouldn't be called Pell's equation. Maybe it should be called the d cubed equation, because it's really both of these famous Indian mathematicians, as well as Bruckner, they all independently discovered it and worked on it. So why is it called Pell's equation? Well, it's because Euler somehow got it in his head that it was something that was invented in this book by Pell, John Pell, apparently. So it's just a complete quirk of, misnaming by a famous mathematician, and it stuck. So we still call it Pell's equations. So what is Pell's equation? It is this: x squared minus dy squared equals to 1, where d is not a perfect square. All right, so this is Pell's equation. All right. So, for example, the cattle problem I was mentioning. This problem from antiquity is actually x squared minus 472, 949 y squared equal to 1. We'll not be solving this one. But that is the problem that Archimedes found. All right. Apparently, in 1880, a fellow named Amthor found the smallest solution, which has apparently 41 digits. Woo! Yowzers. All right, so Let me get to it here. So let's talk about how can we understand the solution to this, all right? So suppose, because there's a very interesting, what makes Pell's equation interesting in particular is that there's actually a group structure defined here. Let me explain. So suppose x1, y1 solves, x1 squared minus d y1 squared equals to 1. All right? Then what we can do is we can factor. See, we can factor this. 1 is equal to x1 plus y1 square root of d times x1 minus y1 square root of d. See that? Well, use your imagination. All right? Great. Now this is where it gets interesting. We can square this. We can square this equation. What has happened? What happens when we square that? Let's work it out. Yeah. Yeah, foil it out if you will. So yeah, we get 1 squared, and I'll write it out. X1. I'll write out. Let me write out a step here. Plus y1 root d. That squared.
X1 squared plus y squared d plus x1 y1 d.
Right.
And then minus the other one.
So you got 2x1 y1 root d, right? Plus y1 squared d. X1 squared minus 2x1 y1 root d plus y1 squared d. All right. So, let's do some algebra here. So, let's see here. So this is going to give us x1 squared plus y1 squared d plus 2x1 y1 root d, x1 squared plus y1 squared d minus 2x1 y1 root d. So if you look at what's going on here, let me just, there's a pattern. We're faced with, let's see here. Let me look at it this way. This is A, right? This is B. This is A again. And this is B. So we're looking at A plus B times A minus B. So algebraically, that of course is A squared minus B squared. Right? But that is specifically x1 squared plus y1 squared d squared minus 2x1 y1 square root of d squared, which gives us x1 squared plus d times y1 squared squared minus d times 2x1 y1 quantity squared. You're like, okay, so what? So what? So that's a solution to Pell's equation. That's so what. Let me point out what happened. What's right in front of us here is that if we put x2 equal to x1 squared plus d times y1 squared, and we put y2 equal to 2x1 y1, you can see from the equation that x2 squared minus d times y2 squared equals to 1. In other words, it solves Pell's equation.
So you get a solution from one solution?
Right, we get, You give me a solution, I can generate a new solution. Give a solution, get a solution.
But is the trick just to always get the first one?
Ah, let's look at an example of this. So maybe you guys can find me the first one. How about this? X squared minus 3y squared equal to 1. Can you find me a solution to this? A non-trivial one. Of course, we can always look at 1 comma 0. Do you guys mind if I go about 10 minutes over today?
That's fine.
I would appreciate it. It would help me finish this. What do you think, Caleb? You got it? Can you guess a solution to that? You got to put x whole numbers.
If you have 0, 1, can you produce one from that? Or is that just a trick a little different?
I mean, just try some stuff. How about we try? We try one. Does 1 and 1 work?
No.
No. How about 2 and 1?
12, no, you can't get a square. You get 15.
Wait a minute. What about 2 and 1? Would 2 and 1 work? If x equal to 2?
Yeah. 2x2, y1. I was doing y1 next to.
So 2 comma 1 I think works because 2 squared minus 3 times 1 squared is 4 minus 3, which is 1. What it is?
I'm taking a picture of you now.
Oh, that's not interesting.
Actually, we're at plus when you're at minus 9. Now we're going to have time to go back.
That's cool. So let's follow what we just, what did the algebra tell us? The algebra says construct x2 equal to x1 squared plus d times y1 squared. Construct y2 equal to 2x1 y1. So, okay, so what is that here?
Well, we get 4 plus 3, 1.
So our x1 was, oh, so you say 4
That's 7.
plus 3 times 1, 7, you said? And we've got 2,
That would be 4.
2 times 2 times, okay, so that's 4.
7 and 4 now.
So allegedly, yeah, 7, 4 is a solution. Does it work? Let's try it out.
Times 3 is
Let's try it out. Is 7 squared? So is 7 squared minus 3 times 4 squared, did it work? Is that actually equal to 1?
16 times 3 is 48, so yeah, it should be.
We got what? Yeah, we got 49 minus 48. We got 1. So yeah, this is very neat, right? And so here's the theorem. Here's the theorem. Pell's theorem, Pell's equation theorem. Pell's equation, x squared minus dy squared equal to 1, always has positive solutions. Always has positive solutions in the integers. All right. And if x1, y1 is the solution with smallest x1, all right, then every solution xk, every solution xk, yk can be obtained by taking powers xk plus yk square root of d is equal to x1 plus y1 root d to the k power. for k equal to 1, 2, 3, and so forth. Now, now there's a little. We've almost proved this theorem, really, with the calculation we just did, right? I mean, essentially, we've shown that we can generate. I mean, we haven't shown. I guess you could worry that we missed something, right? But the trouble here is, the really technical part is that there exists a smallest solution.
Yeah, that's. So if you find a solution but you don't know if it's smallest, can you track back?
You wouldn't know.
You wouldn't know.
You wouldn't know. You could. It would be kind of like working inside like Z500 and getting something that wasn't a generator, but it's like creating like a lot of it, but not all of it.
Okay.
That you could have that kind of phenomena. So I made you guys a handout here. So here's the thing I've been working from. I wanted you to have it. It's my sad scan of chapter 32 of Silverman. And so this just has some beautiful numerics in it, just so you can appreciate that smallest solution. So if you look on page 249 here, it has some different choices of D, all right, some different choices of D, and the smallest solution to Pell's equation. So we were able to figure out for a D equals to 3, 2, 1, with just a little bit of, tinkering. But I would draw your attention to 61. I would draw your attention to 61. I'll write that one up here on the board. So like, look what happens with D equal to 61. Look at that. Look at that. So if you have x squared minus 61y squared equals to 1, you want to solve it. The smallest solution to this is x equals to 1766319,049 if I haven't copied it down wrong, and y equals 226153980. That's the smallest solution to that one. Goodness. Now, this was one of those sort of medieval, math battles, if you will. And so this is apparently, I think this is another one of those things that goes back to Fermat, if I remember right. He describes the history in here pretty well. It's a lovely read. Let's see here. Oh man, I forget where I read it, but I believe it was Fermat who knew that this particular one was quite horrible. Yes, and also the Indian mathematician Bhaskara illustrates his method by solving x squared minus 61y squared equals to 1 more than 500 years before Fermat used this equation as a challenge. Okay, so yeah, in 1657, Fermat challenged fellow mathematicians to solve x squared minus 61y squared equal to 1. And eventually they did find it. And I think that ties into that, like I said, William Bruckner and all that. But anyway, it's really fascinating. There are Pell's equations with relatively small d's, where the first non-trivial solution is just ginormous. And there are techniques for finding the first solution. This is a part, you could easily spend a month of class describing the technical methods to finding the smallest solution. This ties into study of quadratic forms and Pell, Conway's so-called river. If you look at Stillwell, you'll find out that this is easy to understand, and I think it's beautiful, worth our time. But to actually really, really pin down how to find that first solution, to prove the existence, it would be a much, much larger project for us. I just want you to know what Pell's equation is, and to make you aware of this beautiful group structure of it, because I think it's just another feather in the cap of like the algebraic method, that we can use algebra to find new number theory solutions. Anyway, that's it for today. So sorry, I went a little bit over.
No, very good.